DOE CSGF Fellow Brian Corneal in the field of nuclear engineering and engineering physics at the University of Wisconsin-Madison.
I'm Brian Corneal from the University of Wisconsin-Madison, and today I'll be discussing macroscopic plasma modeling and an application to an aspect of Tokamak disruptions. This work was done in coordination with my advisor, Krell. So I'll start by giving some general background, describing what a disruption is and a phenomenon called runaway electrons. And then I'll move into some experiments done by our collaborators on runaway electrons, and then move into simulations that we did to help interpret their experimental results, and then where this work has led from there. So to start, I'll note that magnetic fusion energy is one of the grand challenges in engineering, and one of the approaches taken for magnetic fusion energy is called the Tokamak. The Tokamak has this characteristic donut shape, and as we are moving to larger Tokamak experiments, there is going to be more and more stored thermal and magnetic energy during the plasma discharge. For example, ITER, which is being built in France, is expected to have more than 500 megajoules of stored energy during the discharge, and this is equivalent to 100 kilograms of dynamite. So tokamaks are susceptible to what are called disruptions. This is just a sudden loss of control or confinement of the plasma, and all the stored energy can be released by a disruption on very short time scales, which of course risks damaging the device at these high energies. During these disruptions, there's often rapid cooling of the plasma, which can lead to generation of electric field. To illustrate this, here we have a graph of a disruption from jet showing the current in the plasma, where at this point there's a disruption and the plasma starts to cool, which increases collisions, which increases resistivity, so the current starts to go down. But since plasmas have lower collisionality at higher velocity, the tail of the distribution doesn't slow down as much and can be accelerated by the electric field more easily. And so here you see this region where a very small population of electrons at very high velocity are holding a substantial amount of plasma current for an extended period of time. And then eventually this population of electrons is released. And one can imagine with these high energy electrons, there's potential for damage. They can act basically like an arc welder, and we can see here's an example of actual damage to a beryllium tile from a runaway electron beam that was intentionally generated on the jet device. So one way that we know we can suppress runaway electrons, or that has been studied for suppressing runaway electrons, is called resonant magnetic perturbations. And the Madison Symmetric Torus, an experiment at the University of Wisconsin, has been working on this investigation, trying to better understand the mechanism for this. So the Madison Symmetric Torus has this characteristic donut shape. Some terminology that I'll use, toroidal is referring to the direction the long ways around the device, and poloidal It's referring to the direction of the short waves around the device. You can see here that the device has several X-ray detectors for detecting runaway electrons through Bremsstrahlung radiation, and then it also has a set of magnetic coils here for adding perturbations to on top of the usual magnetic field structure. So Madison Symmetric Torus is able to routinely and reproducibly generate electron populations by operating at very low densities. So just illustrating here, as they go to low density, you start to see the X-rays detected from runaway electrons. And here, as they increase density in the presence of runaway electrons, it increases collisionality and stops them and removes that population. So resonant magnetic perturbations are externally applied magnetic fields that can interact with rational surfaces in the plasma. So what are rational surfaces? To start, tokamaks have a magnetic field that is structured as a set of magnetic surfaces, where these surfaces are traced out by magnetic field lines. An important property of this magnetic structure for magnetic fusion energy is that the field lines are twisted as they go around the torus. And the measure of this twisting is called safety factor, or often uses the letter Q. And Q is defined as the number of toroidal transits a field line takes in order to execute one poloidal transit. So low Q is associated with a stronger twisting of the field. So when the value of Q has a low order rational value, then there's opportunity for that surface to be perturbed or have linearly growing modes. Right? So when these external fields match the helicity, so either these usually come in pairs, poloidal M and toroidal N. So if the external field matches one or both of these numbers, then it can drive that surface and create these sort of island structures that I've illustrated on the right. And these islands can have a strong analogy with what you'll see in Hamiltonian systems, such as like a resonant frequency of a harmonic oscillator, or a pendulum system where you can map out the phase space. And so this plot on the right is looking at a toroidal slice where some of these single colors are single field lines tracing out paths and plotting points on a single toroidal slice. So the experiment found that when they applied a poloidal mode number 3 RMP, they were able to suppress runaway electrons, but poloidal mode number of 1 did not have similar suppression. You can see that with the X-ray counts when they have the applied RMP field. So to understand what's going on in the experiment, we modeled the system with magnetohydrodynamics, ignoring pressure since these were very low thermal energy discharges. And we solved this set of equations with the NIMROD code, which is high performance code using MPI that is able to run on large HPC systems. Through this simulation, we found out that these were sawtoothing discharges. This is a common phenomenon in tokamaks where you have some linear instabilities, in this case, on or inside the Q=1 surface that grow over time, and then they non-linearly interact and relax back to a lower energy state. And so there's this cyclic nature of growth and relaxation. You can see the reorganization of the magnetic fields from this process. It's well understood that these resonant magnetic perturbations can induce islands, and that when magnetic islands grow sufficiently large and can overlap, they will produce a stochastic magnetic field region. This has connections, going back to the connection to Hamiltonian dynamics. This is sort of like a nonlinear Hamiltonian system where there's emerging chaos. So these chaotic field lines allow for particles to readily be transported across the region, whereas the nested surfaces are very good at confining particles. So what we were able to demonstrate is that this m=3 RMP applied for MST in these discharges produced a large stochastic region and edge, since it was resonant with a number of surfaces in that region, and those islands start to overlap. However, the m=1 RMP was mostly resonant in the core, which was already observing these magnetic reorganization events, and so there were still good confining magnetic surfaces in the outer region. We also believe that the sawtoothing behavior is important for the runaway suppression because it can transport these core runaway electrons to the edge where they can be readily lost. And otherwise, the core would be well confining. So the story doesn't end there. We know that particles aren't perfectly tied to field lines. They have gyroscopic motion circling around the field lines, and then this motion can also lead to a drift in the orbit. This is particularly pronounced when there's a large perpendicular velocity to the magnetic field lines, and this is illustrated here in these the calculations from this paper using the core code, where we see the paths of runaway electrons in some other discharge from different modeling, and you can see how the paths wander across many field regions. So we are currently collaborating with this group to work on using this code for our magnetic topologies to better understand the transport of runaway electrons. So in summary, these runaway electrons need to be suppressed in order to mitigate the effect of them in disruptions, and that there's experimental evidence that the appropriate helicity of RMPs can be used to suppress runaway electrons. Our modeling has helped explain why different helicities would or would not suppress runaway electrons in these particular MST discharges. And we want to do further modeling to get more information that will give us a more complete understanding of these results. I'd like to thank the Center for High Throughput Computing at the University of Wisconsin-Madison for providing the computing resources for this work, and the Department of Energy and DOE CSGF for their financial support. Thank you.